Okay, I'm not sure this is the equation we started with. Divided than xy squared, I don't see how that would give you a vertical asymptote either geometrically, but you do the solution and you see why it happens, and we certainly saw that it happens. Okay? So I don't think I have the right equation here. Because if you solve this equation in the first place, we get something that I don't think we've seen before. Very simple to solve. Okay, so let's solve this equation, then see how the solutions will be consistent with this direction field.
I don't know what it was. I was trying to look it up.
Yeah, well, don't worry about it. This is as good as anything. And we, probably assign you to go ahead and do a direction field for the equation we actually used. We can just go back to what I posted and find it, okay? But we're not going to investigate that right now. So my point is, let's say we just want to start here, okay? Well, we don't have the slope field down here, but we do understand that the slopes are going to all be 0 on the x-axis as well as on the y-axis, right? Because if x is 0, your slope dy dx is 0, okay? Okay, so we're going to have a very small slope here, but by the time we get out here, the slope is probably, we're going to go up a little bit. The slope will be kind of approaching this, really be about half of what this is. So it's probably going to come out something like this. And a little bit of slope here. As we move out here, we're going to keep increasing, and it might well be that we go through or near this point, and then things are going to get real steep, right? Does that make sense? You just follow the trend of these curves, and if we start here, well, again, not much slope to start out, but pretty soon we've got some slope. And then as we approach this point, we might well miss that, and it might go up very rapidly, right? Okay? So you see there are possibilities of asymptotes. And maybe we do get an asymptote, but we're going to get an exponential solution. Okay. It's a steep exponential, and we're going to see how that works. So let's do it. Okay, this equation clearly is separable, so we can have dy over y equals x squared dx. So that natural log, the absolute value of y equals x cubed over 3 plus some constant. And then you do the arithmetic, tells you the absolute value of y is the inverse function, applying the inverse function and so forth. We get this, right? And that can be written as e to the c times e to the x cubed over 3. Now, I wrote 2 there instead of a 3, but correct that, okay? Where c is arbitrary, well, this means that this is absolute value of y, right? Okay? So it'd be possible that y would be a negative multiple of the exponential, right? You could get a negative exponential. Or you could get a positive exponential. Now, e to the c is always positive, right? So we would have absolute value of y equals a e to the x cubed over 3, where a is greater than 0.
So you can just replace an arbitrary exponential with an arbitrary
Well,
linear?
what's e to the c? What are your possible values? What's the range of the function e to the x?
0 to infinity.
Okay, so this would be anything from 0 to infinity, right? Which means you can replace it with an a which is greater than 0. Make sense?
Yeah.
So an e to the c, when c is arbitrary, is any positive number. So there's no point in keeping c there or e to the c to confuse the form of the thing. We can write it this way. Okay? Well, this means that y could be plus or minus a e to the x cubed over 3, right? If the absolute value of y is this, then y could be plus or minus. And this just goes back to pre-calculus, which you probably want to refresh. It's not absolutely clear. And if you're tutoring pre-calculus, there's a reason we do this, okay? There's a reason we do absolute values, and that's going to be coming up in those courses pretty soon. Next week, probably. So if you have somebody come in asking about absolute values, make sure you have a little perspective. You know what to tell them, but they need to be prepared to do this. Although most of them will never need to, some of them might, okay? Every semester I have pre-calculus students who can be engineers. Most of them don't want to work that hard or have other goals for other reasons. One way or the other, any pre-calculus student needs to understand absolute values well enough to understand what I just said, okay? At least for a while, so that the seed is planted in their brain, and the next time they see it, they say, oh yeah, I remember that, okay? Okay, well anyhow, that's an aside, but okay, so now we have this solution, right? Okay, so if y of 0 equals 1, well, this is either always positive or always negative, right? Because e to the x cubed over 3 is always positive. So if this is always positive, then we know that in this case, a has to be positive. In fact, we can tell that it has to be 1. Okay? But another way to do this, we don't have to worry about the plus or minus. What I just said kind of shows us that it takes care of itself. A can therefore, this A can be replaced by an A that can be either positive or negative. Okay? Now you really want to understand that, because there are a lot of differential equations that end up with solutions of very similar nature. In other words, this is a reasoning process you're going to use again and again. Starting now. Okay? Well, now we can see what the exponential is. Now, first of all, what do you know about exponentials? They get really steep really fast. And if you do an exponential of an x cubed, even if it's over 3, that exponent gets big really, really fast. Right? Okay? So, what else do I really want to say? Well, in this case, solution is this, and that's totally consistent with the shapes you get when you do this graph. Okay? I'm a little disturbed by this. Okay, I'm no longer disturbed. Okay. Derivative of e to the x when x is 0 is not 0, right? But the derivative of this is 0, because of course you apply the chain rule, you get an x squared e to the x cubed over 3, right? And when x is 0, that is 0. So for a minute there I had a moment, I said, wait a minute, something's wrong here, because I'm a little bit stupid and wasn't thinking ahead. But then when I checked this against common sense, I contradicted my original common sense by a little deeper insight, although there's nothing deep about any of that. The deep thing is checking your dang solution, which I keep nagging you guys about because you're not real good at it. Okay? Getting better. And good enough. You're going to have to get better as you continue, so get in the habit. Okay. Make sense? Now, what's the direction field look like if we go backwards a little bit on the edge? Like if we go to x equals, let's just pretend -1 was here. I didn't leave myself enough room, but let's just pretend that's -1. Should be a little further over here. Okay? I could draw it back here, but that would look weird. Okay? So, x equals -1. What about -1, 1? What's the slope?
-1. Wait, no.
X is -1 and y is 1.
You're right. That's just 1.
X is 1. Not x is 1. The slope is 1. X squared y is 1. X squared is 1. Okay? So we can very quickly see that at this point, the slope is going to be the same as it was over here. Okay?
So is that solution y equals e to the x cubed over 3 just between x equals 0 and infinity? Because it's not an exponential, or not the same exponential to the left of the axis.
Well, we're going to look at what happens. Okay, first thing I want to show you is that the direction field is symmetric. Okay, but not symmetric by reflection. The direction field on this side isn't a mirror image, because a mirror image would take you over to a negative slope, right? But there is this type of symmetry here where the direction field is kind of like this. In fact, the direction field of this equation and I'm not drawing it exactly, okay? But it keeps getting steeper as you go out here, and it kind of gets rapidly steeper. Okay, well, it does the same thing over here. Not by reflection. In other words, the slope here is not like this, corresponding to this point. The slope is identical to what it was here, and you can see that in the equation. And you need to develop an ability to sketch these fields and match them up with different equations. Okay? And it gives you, a little deeper insight into everything you've learned in calculus and pre-calculus. Well, not everything, but a lot of what you've learned. So the field is going to kind of look like this. Okay? As you go to the left, you repeat these slopes. Why? Because the square of -x is the same as the square of x. So the x squared will give you the same numbers at equal distances on either side of the y-axis. The y values, of course, are the same. Now, if you go down here, what happens? Just looking at this expression, what's the direction field going to look like below the x-axis?
It'll be a mirror image.
Yeah, it is a mirror image because y becomes negative, right? So you have y values of the same magnitude down here, but unlike what happens between here and here, where the x squared has the same magnitude at equal distances from the y-axis, or it has the same value, the y has the negative value, which makes all the slopes negative, right? So what you have is still 0 slopes on any of the axes, right? But down here, it's going to look like this. And same thing over here. It's going to be an upside down picture of this. Okay? And you can practice drawing these things. This gives you a picture of what the solutions of your differential equation are going to have to look like. It's not precise, although the more points you use, the more precise your approximations can be. And you can compare your approximations with the actual solutions. So you kind of expect some problems of that nature. Okay? So if we start at a point down here, what happens? Okay? Start at a point over here, what happens? That's going to actually be pretty steep, so we're in the really steep part of this curve. And of course, we can always project these curves backwards. Okay? And what happens then? Well, okay, let's go back to, let's say, this curve right here, which we saw kind of does this. And we project back, or we go back to the x-axis where it levels off, right? Then what happens? Well, then the slopes become like this again, right? So we're going to have something like this. Okay? And I should have changed my concavity a little earlier. I hadn't changed it, and I should have. Because what's going to happen now? Okay, it's going to get steeper here and steeper here, but as we approach the x-axis, the slope levels off, and we end up with something like this. Now, does that make sense for the graph of e to the x cubed over 3? Well, x is going to be negative, so x cubed is going to be negative, right? And if x cubed is negative, then what's going to happen to the value of y?
It's going to get smaller.
Yeah, because e to a negative power is a very small number, right? As the negative power gets big, the e to the negative power gets very small very quickly. So it's going to level off and approach 0. Okay? And over here, same thing's going to happen. It's going to do this, it's going to approach 0, but it's going to do that. You're going to have a symmetry in your solutions. If you start at a point down here that's a reflection of this point, which I just coincidentally did, that's what it's going to look like. You come over here, what's going to happen? It's just going to level off really fast. Okay? And you're not going to have a change in concavity. Now you should. Now see how you could. So you can do a second derivative test on this and see what happens to the second derivatives, especially if x is negative. Okay? You will eventually, well actually you will have a change in concavity. This thing is going to go down really fast.
It's kind of just like a normal exponential, but has the hump in it.
I'm sorry?
It looks like just a normal exponential that has the hump in it.
Yeah, well, yeah, it is a normal exponential, but again, because of the fact that you don't have just the x here, okay? And you know what the normal exponential looks like, it just, you know.
Yeah.
Yeah, and you recognize that. So you what you're saying is that somehow this deforms your normal exponential function,
If you increase,
which is a good observation.
if you increase the power, if you change it to be like x to the 5th or 6th with it.
Well, first of all, an odd power is going to behave differently than an even power.
Yeah, but like.
So just take higher and higher odd powers. It's going to get, it's still going to go through here, and I didn't really quite draw a level here. It's still going to level off right here. It's going to have a horizontal
Yeah.
component, or horizontal. The graph's going to go horizontal for an instant. You're going to have a point of inflection. Your concavity is going to change, right? And it's just going to be steeper. It's going to get steeper faster because if you have a higher power of x, a higher even power of x, which will give you an odd power down here, you're just going to have an argument of your exponential that increases much more quickly.
It wouldn't like give you, it wouldn't give you multiple inflection points, giving you
No.
like multiple changes.
No, and that, I mean, that's really good. It's really good that you're thinking about that and you're looking at that, and you can check that out by figuring out your inflection points. Matter of fact, since you bring it up, let's go ahead. What's the nature of this solution? Derivative is this, right? Okay, and that derivative is never zero, except at x equals 0, right?
You're missing a 1/3.
No, wait.
No, because if I take the derivative of x cubed over 3, I get x squared. Think about it, okay? And you get a little more used to the chain rule, but you will, because you're going to be doing a lot of derivatives, okay? To check yourself. Okay, so you get this. Got a critical point at x equals 0, okay? And it turns out that that will be an inflection point, because if you take the second derivative, well, I'll just do this, 2x plus x to the 4th e to the x cubed over 3, okay? And it's 0. When 2x plus x to the 4th is 0, right? Which means 2x plus x cubed, 2. Okay, this is 0. At x equals 0, or x equals 2 to the negative 1/3. Okay? And I guess it's negative 2 to the negative 1/3. Should be plus or minus. Okay, I did. Yeah. Trying to do something in my head with no head. You got 2x plus x to the 4th equals 0. That factors into x times 2 plus x cubed equals 0. So x cubed equals 2. X equals 2 to the 1/3, cube root of 2, right? So I'm right. But there's an inflection point on this side. Which I'm missing. But you're sure not going to get a plus or minus out of a cube. Yeah, I'll let you guys work it out. Okay. So, you understand what I'm doing? Okay, so at 2 to the negative 1/3, and 2 to the negative 1/3 is approximately 1.27 or something like that. A couple of question marks on that. 1.3, yeah, probably not too far off. Okay, take your calculator and see how stupid I am. Okay, but somewhere around 1.27. I swear. There's clearly an inflection point here. The concavity changes, right? And clearly an inflection point over here, but that's at like, oh, wait a minute. 2 plus x cubed equals 0. X cubed is negative 2 to the 1/3. Remember to be more careful than I am. I won't even tell you what I did when I hooked up my gas water heater. But house didn't quite blow up. Little explosions, no, not really. Forgot to tighten up something I'd loosened earlier. Kept smelling a little bit of gas. Wasn't, finally figured out what it was, fortunately. I shouldn't be doing that stuff anymore or something. Okay, now, so we get negative 2 to the 1/3. So here are inflection points, right? Inflection here slightly to the left of x equals negative 1, right? Implicitly, that's your negative 1. There you go. Actually, it's not even to scale, but you get the idea. Okay? So what you're just saying, Alexander, there it is. Now, if it was an x to the fifth here, instead of an x cubed, you'd have an x to the fifth over 5, right? So you'd have a 5x to the fourth plus x to the eighth, which would give you a negative fourth root of 5. Which would put your inflection point somewhere else. That should actually be closer with that, so I probably said something wrong, but you get the idea. That makes sense? Just using your standard first semester calculus, critical points, inflection points, maximum and minimum. And there's no max or min. There's a limit as x approaches negative infinity, but there's no min. No relative max, no relative min. So it has all these characteristics that can be related back to the differential equation. Okay? And you want to understand as many of those relationships as you possibly can. Which means that when you solve one of these things, with whatever time you can carve out of your obviously busy schedule as engineers, tutors, and whatever else you happen to do with your time, it's going to be worth your effort. Make sense? Good heavens, 26 minutes on that.